In this lecture, we're going to talk about linear elastic fracture mechanics applied to cyclic loading for fatigue. Now, before we get into that, let's just review some of the basics of linear elastic fracture mechanics again that we've covered in some of our other lectures, but just want to make sure I haven't missed anything, and it's always worth repeating some of these items. So we ended up talking about how we have a stress intensity factor K that we can compute based on some sort of geometry factor that depends on the dimensions of the crack in the body that you're looking at, some remote stress, sigma, and then the square root of pi times some kind of crack length parameter. So for an example, if we have an infinite plate with a far field stress of sigma that has a internal crack of 2a in it, then the geometry factor would be 1, and our stress intensity factor would be K is equal to sigma square root pi a. Now, we don't usually have an infinite plate. What that really means is we have a very large plate in comparison to the dimensions of the crack. But if we have a finite width plate, or the crack is kind of large in comparison to the width of the plate, then we can come up with a non-unity geometry factor. Let's see if I can call a few of these up for us to take a look at. Here we have them on this page. And so our geometry factor f of g in this case would be given by the square root of the secant pi a over 2b. 2b is the width of the plate. If we have an edge crack, then we have a geometry factor that's a little bit different. It's 1.12 minus a term a over b, another term a over b squared, another term a over b cubed, another term a over b to the fourth. In fact, this is a series, and that a over b, a is the crack length and b is the width of the plate. Typically a would be small in comparison to b, so as we get higher and higher orders of these terms, the change from 1.12 would typically be very small. Here's a double edge crack plate, and here's a bottom edge crack for a beam in bending where you have the bottom surface in tension. For fatigue, we often have cracks that initiate at the surface, and so this geometry factor of 1.12 is going to be fairly significant for us, but we'll see that here in just a few moments. So kind of keep that in mind. Another thing that we have going on for us in fatigue is that one way or another, most fatigue cracks will turn to be a mode 1 type loading. So a tensile type loading, as opposed to the shear loadings for mode 2 and mode 3 that we've discussed in the previous lectures. Let's come back to the previous page then. So we have a way to find out what our geometry factor is. There are sophisticated ways to find this, but most typical geometry factors are tabulated in large handbooks. So if we know f of g, we know the stress. If we know what the crack length currently is, then we can compute our stress intensity factor. And we talked about previously that when the stress intensity factor reaches a certain critical value, then fracture occurs. Typically, we'll use K1C, which is the plane strain fracture toughness value. And we talked about how as you shift from plane strain to plane stress, you actually gain a little bit of increase in your critical stress intensity, but the material property is the minimum, the plane strain fracture toughness. We also had some lectures where I asked you to take a look at either the derivation of the equations for the stress fields ahead of the crack tip or the plastic zone shape ahead of the crack tip, so we can take a look at those as well. And just as kind of a refresher here, if we were to look and put a coordinate system at the tip of a crack, and we were to plot the stress sigma and the radial distance from the tip of the crack, we would typically see something that goes like this shape with those equations. And the stress would tend to infinity. The stress follows an equation that looks similar to this. K, whatever our stress intensity is, divided by 2 pi r, where r is the distance ahead of the crack tip. So when r goes to 0, then we have a singularity of power 1/2. Okay, it's a square root r singularity. And this flattens out to, in the far field case, the value of the remote stress, sigma. It's kind of small there, but and this kind of flattens out at that level. So as we get near the crack tip, this really increases. Now, a material cannot sustain an infinite amount of stress. So one of two things will happen. When it gets high enough, if you have a brittle material, the brittle material will fracture, the crack will extend. And if you have a brittle material, the energy released during the fracturing can keep that crack running. So think of a plate of glass. If you have a small crack in glass, kind of like our picture over here, and you were to pull on it in tension, the crack would run through to the edges of the plate. And it might even bifurcate if there's enough energy available released during the fracture process. Well, in our class, where we're primarily looking at metal fatigue, metals behave a little bit more differently. They will tend to yield instead of fracturing without stop. Okay. So ahead of the crack tip, we may have a little bit of a yield zone where the stress is effectively flat for a little while, and then it comes down and it kind of rejoins this shape of curve. Now, does it look exactly like this picture that I've sketched? Well, probably not. Some materials experience hardening, so the stresses may still be yielding, but the stresses may increase a little bit over here. It may kind of flatten out and kind of come down and join this curve. But what I've drawn is kind of an idealization for what's called an elastic perfectly plastic material. And an elastic perfectly plastic material, if we looked at its stress strain curve, it would come up, it would hit some value of its yield stress and basically move over flat. Oops. Let's say elastic perfectly plastic. So let's talk a little bit about the size of this yield zone, and we can talk a little bit more about the shape of it in more than one dimension as well. All right, so you've seen some of my previous videos in which we've characterized the shape of the plastic zone based on the von Mises yield criterion for ductile materials. And we said that kind of in 2 dimensions, this is not the same plot that I've drawn here. In 2 dimensions, it kind of takes a shape that maybe looks something like this. And it's yielded up until some certain level here, and you can make this contour based on the von Mises yield criterion that we talked about. Now, even this isn't completely right, because the equations that we've based this on are linear elastic fracture mechanics equations, and we've just set the value of that zone equal to whatever the yield stress is. So it's not completely right, but that gives you a pretty good shape, estimate of the 2-dimensional shape for what it is. Now, what we're looking at in this first picture, if we were to think of this size right here, would basically be this part of it right here. Okay, so this red circle and this red circle correspond to about the same thing. And so an easy way to characterize the yielding ahead of the crack tip would be like the diameter or the radius of this zone right here. Now we have another thing that goes on when we look at plane stress versus plane strain. I'm going to see if I can draw this sketch. If we were to look at something that was shaped like a compact tension specimen or a very thick plate with a crack in it, again, I'm going to try to do my best to sketch this out. It can be a little tricky in 3D without having a ruler or anything like that to use. Now let me try to draw the crack plane in a different color. Okay, so this line joins the crack plane on either side. If we were to look at the plastic zone size on the outside edge of this thick piece of material, the plastic zone size would be about the same on either side, but it would be significantly different in the middle. In the middle of this object, the plastic zone size would tend to be quite a bit smaller. Okay, so the takeaway from this is that under plane strain conditions, plastic zone size is smaller than in plane stress conditions. So why is that important? Well, for linear elastic fracture mechanics, the smaller the plastic zone size is, the more applicable linear elastic fracture mechanics is. There's another entire branch of fracture mechanics called elastic plastic fracture mechanics, in which you deal with finite plastic zone sizes. It's a little harder to deal with that. The math, the application of linear elastic fracture mechanics is a lot easier. And so if you can make life easier, then that's a good thing. So the smaller the plastic zone size, the more applicable linear elastic fracture mechanics is. Now we can characterize the monotonic plastic zone size. And so I'm going to draw some figures, and I'm going to talk about this value here, 2 sigma yield for this zone size right here. All right, so in monotonic conditions, what I mean by that is you just take your material and you pull on it until something happens, it breaks, or you get significant yielding at your crack tip or whatever happens. For plane stress situations, we have a larger plastic zone size, 1 over 2 pi k over sigma y squared. Again, this is an approximate formula. Don't take this completely seriously, but it gives you a good idea or feel for what's going on. And for plane strain, we have 1 over 6 pi k over sigma y quantity squared. Now for the cyclic plastic zone size, we get some similar values, but they're in fact even a little bit smaller. Let me write these down and then we'll talk about it. Because of the Massing's hypothesis and the Bauschinger effect in our material, we effectively replace sigma y with 2 sigma y. And the plastic zone sizes are 4 times smaller than they are for either plane stress or plane strain. So in plane stress, we have 1 over 8 pi k over sigma y quantity squared. And in plane strain, we have 1 over 24 pi k over sigma y squared. And this is due to the fact that around our plastic zone size, we have a lot of elastic material restraining that plastic zone. Due to the constraint of the surrounding elastic material. Now, what does that mean for us when we take a look at metals that are subjected to cyclic load for fatigue? Well, that means in a lot of cases where you might not think linear elastic fracture mechanics would apply, we actually have an extended range of applicability of LEFM due to the cyclic plastic zone size being smaller. The smaller the plastic zone size is, the more applicable linear elastic fracture mechanics is, so we can extend the usefulness of LEFM. Okay, so we'll keep that in mind as we look at high loads and lower loads on materials with cracked bodies. So now let's talk a little bit about fatigue crack growth. So again, we're kind of like we're looking at the side view of our specimen here. Maybe like a compact tension specimen or a plate with a crack. And we start to grow this crack. So it starts out with this size and then it extends, grows a little bit, maybe grows a little bit more. So we can think of the initial crack length, and we can think of maybe a little delta A for each subsequent extension of this crack. I've had to exaggerate this in order for me to be able to draw this picture. But that delta A would be the crack extension. And this crack would grow per cycle. Now these individual increases in the crack length per cycle are called striations. Well, at least what you would see if you were to look at that surface would be these individual striations. You can't see these with the naked eye. You have to use a very good microscope. You have to use usually a scanning electron microscope in order to see these individual striations. Now these individual striations, the growth per cycle, they're not usually going to be constant. There may be some regions where you have a little bit of constant growth. There may be some larger striations and some smaller striations. Depends a lot on the material composition. If you're breaking through particles that are inside the material, or if you're just kind of growing through a material that's pretty homogeneous, then you can get different effects. But also remember, keep in mind, that the stress intensity factor is the thing that determines the amount of crack growth that we have. That stress intensity factor is determined by the current crack size. So even if the stress stays constant, if your crack is increasing in size, your stress intensity is increasing. All right, so for this reason, we're going to be interested very often in the change in the stress intensity. So instead of our previous problems in the stress life approach, where we looked at cyclic stress, or we looked at cyclic strain, now we're going to be interested in cyclic stress intensity factor. Or delta K. All right, so all the similar terms that we've talked about still apply. So we can have a maximum stress intensity, we can have a minimum stress intensity for the cycle, and then the stress intensity factor range would be the maximum minus the minimum. We can take a look at a material and kind of observe what happens as a crack grows. We were to plot stress intensity factor on this axis and the growth per cycle on this axis. Okay, instead of using delta A, I'm using a dA by dN. It's a crack growth per cycle. And we do this on log scales. Here's our log scales again. We would make some observations. Usually you wouldn't have any crack growth, any appreciable crack growth, until you reach a certain level of stress intensity range. So this doesn't start over here, this would start over at this value right here. And again, remember this is on log scales, so these are kind of small numbers in between up here, and the numbers get closer together up here. But there would be an initial growth that might be kind of rapid, at least it would look rapid on this plot. It would kind of go nearly vertical. And then after a little while, on the log-log plot, it's fairly straight and consistent. Kind of a straight sloped line on the log-log scales. Now we know what kind of equation that is. That's a power law equation that would fit this region right here. And then as the crack gets very large and it's almost ready to break through to the other side of the specimen, in order to crack your specimen, you have impending rupture. You have what's called unstable crack growth, and this kind of accelerates again, so it kind of picks back up. So there are three distinct regions that we have that we can identify. Call this region 1, and maybe over here, region 3, and in the middle we can call this region 2. Region 1 would be initial crack growth. So it can include initiation and the growth of a small crack. 2 would be stable crack growth. And region 3 would be unstable crack growth and fracture. All right, remember again, we're on log scale. So if we initiate the crack over here, there may be a few hundred cycles where we have this kind of rapid but kind of decelerating crack growth. In comparison to what goes on in this region, this number of cycles is probably insignificant. The initiation, the time it takes to initiation, well, we can incorporate that with our stress life or our strain life approach to fatigue. Okay, so we're not really going to worry too much about region 1 for fatigue crack growth, or for the fatigue life of the specimen. Region 2 is pretty interesting because it has kind of this steady, constant growth, stable crack growth. So this is going to be our main region of interest. And in region 3, the unstable crack growth and finally rupture of the specimen, again, this can be a very few number of cycles, and your usefulness of your engineering component really kind of ends when this region starts. So we're going to ignore region 3 as well. So we're going to focus on region 2. Now, again, because these are on log-log scales, we can write a power law type relationship. We've seen this already a few times in our class, where we have these kind of power law relationships. And in this case, the variables of interest are the crack growth rate, dAdn, some coefficient, and delta K to the m power. The C and the m are material constants. They're material fitting constants. For this region 2. Now this is called the Paris crack growth law, or the Paris law. Paul Paris was one of the early researchers in fatigue crack growth. There are some good stories about how he tried to get this published and he couldn't get a mainstream journal to publish it. He finally got someplace to publish it, and basically it spawned an entire subdiscipline of mechanics and material behavior taking a look at stable crack growth. I went to school with his son at the University of Illinois, and he had some interesting stories to tell. So we're going to focus on this part here for the stable crack growth. Now, if we want to know the number of cycles that it would take, we can separate our variables and integrate. All right, so we have dAdn is equal to C delta K to the m. We're going to separate this out. Okay, so then dN would be equal to dA divided by C delta K to the m. And if we wanted to find the number of cycles, if we knew these material properties, we would integrate this from some initial crack size to some final crack size. And that's not a terribly hard equation to deal with, but always keep in mind that that delta K depends on the crack size. So it's not just as easy as integrating a constant. We do have to keep in mind that delta K depends on A. All right, so let's, I think we have enough room here. Let's write this on the other side of the page. So first thing we'll do is just rewrite this. and we'll put in whatever our delta K is. It's a geometry factor. Delta sigma square root pi a, all to the m power. Now, not only do we have an a in there from the square root pi a, but the a, the crack size, can also appear inside the geometry factor term. So we can make a little note of that as well. A can also influence f of g. And in complicated situations, then you have to take that into account. But if you recall, one of the things that we mentioned was that most of our fatigue cracks will quickly turn to mode 1. They will be on the surface of the component where the crack initiates. And if it's a small crack, then the geometry factor is going to be about 1.12. So as a simplification, we're going to take f of g to be about 1.12. And it's kind of interesting, one of the things that I do when I teach fracture mechanics is that we go through the very detailed process, and then we compare our results, the detailed process where the geometry factor can change, and we take that all into account. And then we take the shortcut where the geometry factor is 1.12, and we take a look and compare the results. And in a lot of cases, this assumption of 1.12 works out very well. Some cases it doesn't, but with experience you kind of learn to know when those are. Well, the reason why we want to do this, though, is that it's going to make our life a lot easier when we want to come up with a simple formula for crack growth. So let's rewrite this again, pulling out the things that we're going to assume are constants. All right, I didn't leave enough room to the left. I'll write the things out to the right. We're going to have a C, we're going to have an f of g to the m, we're going to have a delta k, a delta sigma to the m, we're going to have a square root of pi to the m, and then inside we're going to have an a to the m over 2. All right, now let me use a clean page. All right, and again, another assumption that we've made is that we have a constant stress that we're subjecting our component to. All right, so basically we're integrating a to the minus m over 2, and when we integrate, we add 1 to the exponent and divide by the new exponent. So I'm going to write down what we end up with here. To simplify this a little bit, I'm going to write this as 2 divided by m minus 2. We have the c, and this is the divide by the exponent term. We have c f of g delta sigma square root pi all to the m. And then instead of writing this as the final minus the initial, we're going to write this as the initial minus the final to take into account the negative sign that I'm not writing in here. If this doesn't make sense, just do the integral and you'll see where all these terms come from. We have 1 over the initial crack size. On the bottom, m minus 2 over 2. And then we have minus 1 over the final crack size, m minus 2 over 2. All right, so let's take a look at this for a little bit. We're going to run into trouble if we end up with our material constant equal to 2. All right, so you will see m often in the range of 4. If you end up with a m is equal to about 2, see if you can find another pair of fitting constants that work for your data. Usually these fitting constants are not unique. Okay, so you'll often see in this formula written down, and then, okay, you just don't take m is equal to 2. We've assumed that we have a constant geometry factor, a constant stress range. Of course, pi is constant, and then here we have to the m power. Here's the c. The c is usually a fairly small number. Depends on if you're in meters or millimeter type units. So I'm going to put here, watch your units. And in this other term, this is kind of interesting. We have an initial crack size, which is usually really small. Then we have a final crack size, which is usually kind of big. If you take a big number and you take the reciprocal of it, then this is very small. All right, so to write that down, the number of cycles for fatigue crack propagation is usually insensitive to the final crack size, relatively so. But the number of cycles of crack propagation is usually very sensitive to whatever you choose as your initial crack size. Now for the final crack size, it's not too hard to come up with an estimate. We remember we had our formula that k is equal to f of g sigma square root pi a. And if we wanted to find out a critical crack size, then we would make this a sub c, and we would put in here k1c. So we can use our critical crack size for impending fracture to be our final crack size in our integral. Now for our initial crack size, what do you use? You use 0.1 millimeters? Do you use 2 millimeters? 5 millimeters? Well, the best thing to do with the initial crack size is to actually measure it. You can make some assumptions. So when you do a stress controlled fatigue test, well, like the rotating bending test, that's over when it fractures in half. So the crack propagation is really kind of built into that, but the crack propagation life is fairly small in comparison to the total life of the component. When you do a strain controlled test, well, you often stop that test when you experience a drop in load. The drop in load is caused by a crack or multiple small cracks initiating and being present on the surface. If you can measure those, then you can use that for the initial crack size. If you want to, if it's not a safety critical calculation that you're doing, well, then maybe you can use 1 millimeter or a half millimeter initial crack size, and that would probably give you a pretty good estimate. In other instances, like if you were doing aircraft analysis, well, in aircraft they usually inspect the components quite frequently. If they detect a small crack, then they would use that size. If they do not detect a small crack, then the safe assumption would be to assume that the initial crack size is the minimum detectable flaw size. right? So in non-destructive testing and evaluation, maybe ultrasonics or X-ray or what have you, there's a certain limit to the size of the defect or flaw or crack that you can detect. Maybe it's 0.1 millimeters. Okay, so if you don't see any cracks, well then you to be safe, you'd want to use 0.1 millimeters. If you do see a crack in the structure, then you would use the actual crack size. And so a lot of things that we talk about with fatigue crack growth kind of parallel what we've done for stress and strain life. We can talk about R ratio effects. Now, we can define the R ratio in stress controlled loading as the minimum over the maximum stress in a time history. Well, in the same way, we can define an R ratio as a minimum stress intensity factor over a maximum stress intensity factor as we look at our waveform for our stress. Now, right now, we're still looking at constant amplitude loading. We're going to take a look at variable amplitude crack growth loading in a separate section where we cover variable amplitude loading in general. But we can take a look at our plot of crack growth and stress intensity factor, similar to what we've done before, where we have the log delta K on the bottom axis and the log dAdn on this axis. And you can measure this, so you can do different techniques to measure the crack growth rate and the stress intensity factor in the lab. And if we're only going to look at the stable crack growth region, that's kind of the straight slanted line on this plot, our R is equal to 0 loading may look something like this. Okay, so R is equal to 0 would be our minimum coming down to 0, so it would look something like this. We could take a look at R greater than 0. Let's see, with an R greater than 0, we're going to be a waveform, I guess, like this. And as expected, we would tend to have shorter fatigue lives. And we take a look at R less than 0. And we would tend to have longer fatigue lives if we think of the delta K being this entire range right here. So as we move over this way, we have shorter. As we move over this way, we have longer propagation lives. Now there are ways to take into account kind of the R ratio effect in fatigue crack growth. And there are a lot of different formulas that people have developed. One of them is called the Foramen equation, and it modifies the crack growth. The standard dAdn is equal to C delta K to the M formula by terms that deal with the R ratio. So it's 1 minus R K sub C minus delta K. And there are others as well. There's the Walker equation. it's not an M right here. That's actually another different material parameter N. So again, these are all kind of empirical type constants. It's a reminder the Kc and the K1c, plane strain fracture toughness here, and then whatever you're at over here, or your actual thickness to get your Kc. Okay, the point here being basically what you're doing is you can think of this as altering your coefficient that goes in front of your delta K to the M. Well, another term we need to talk about then is something called delta K effective and something associated with crack closure. So the basic idea is that cracks can only advance when they're open. So if we were to look at a waveform like this, where we have our stress intensity factor versus time, and we talked about how this was the maximum, and this is the minimum down here, and from here to here is the stress intensity factor range. If we are really going into this negative minimum side of our stress intensity factor, there's only a couple ways. One way you can do that is if the stress is compressive. Okay, the crack size is going to be the crack size. The stress goes negative, then you have a negative stress intensity factor. Well, that crack really isn't growing when the crack surfaces are pressed together. So you might think, well, maybe there is only an effective stress intensity factor range when we go 0 to maximum. Okay. And so that could be a way to come up with an effective stress intensity factor range. Another thing to keep in mind, though, is if you're really cycling tension and compression and you're pressing the crack surfaces together, you could be taking a tensile plastic zone and creating a compressive plastic zone in front of the crack tip with that reversed loading. And to overcome that compressive plastic zone ahead of the crack tip, you actually need a little bit more tensile stress than just 0. So if your waveform looks like this, it's possible that your opening stress intensity factor is not at 0, but it's somewhere above on the tensile stress side. So whatever this is would be delta K effective. Now the trick here is determining what the opening stress intensity factor is going to be. And when we get into variable amplitude loading, we'll be able to come up with some estimates. It also changes in time. So if we have a crack tip here, we generate a plastic zone size. We compress the crack tip together. We have these compressive stresses now ahead of the crack tip. And then we open it up again. It doesn't really open until we have enough stress intensity to overcome this residual plastic zone. But once we grow through that, we're kind of into new material and we're starting the process over again. So the effective stress intensity factor range, the K open, it may change as the crack grows. Okay, so again, this is just one of these tricky things about fatigue crack growth. When that is important. So take a look. Maybe a safe estimate here would be to use 0 to maximum as a stress intensity factor range. You usually don't get into too much trouble when you overestimate the loads. When you underestimate the loads and stress intensities, then you can be non-conservative on your life estimates. If you're too conservative on your life estimates, then you've built in too much margin. You have extra weight in your structure that you don't need. So there's always this engineering trade-off between a good assumption and a bad assumption. We will investigate crack closure and delta K effective a little bit more again as we get into variable amplitude loading, and we have some models that can take care of that as a function of the load sequence. The last thing I want to mention in this lecture then are a couple ways that we can measure crack sizes. All right, so in kind of what I would say normal semesters, I would take students down to the lab, we look at the testing machines, we look at the traveling microscope, and what we can do is we can do optical measurements. On a specimen, usually a compact tension specimen, but it could be other type specimens. But we can get into the lab and see how much this crack grows after a certain number of cycles. Now, like I said, you're not going to use a regular microscope and see individual striations, but over 1,000 cycles, you might be able to say that the crack has grown 0.1 millimeters or something like that. It's just fairly labor intensive. In fact, let's get rid of the word fairly, and we'll just say it is labor intensive. You have to have somebody sitting there keeping an eye on the situation and making notes and measurements. There are other ways you can kind of take a look at. You can look at compliance measurements. Right, so if you have a small crack in a plate, if you look at the stiffness, the load versus displacement curve, it may be fairly stiff. If the crack grows, then this curve will be a little bit less stiff. Again, I'm just doing this as kind of a sketch, as a cartoon, and not anything that you can measure. But as the crack size increases, then this gets a little bit more flexible or less stiff, more compliant. You could use crack gauges. They're similar to strain gauges. The idea is if you have a crack, and ahead of this crack you put a grid pattern of individual wires. As this crack extends into this grid pattern, you will start to change the resistance of this pattern. You'll break through these wires and the resistance changes. You may need to initially calibrate this optically, but after you take the one measurement, then you can have an idea of how much that grid pattern has been broken as it goes through. There's some advantages and disadvantages of this approach. And the last method that we'll talk about then is potential drop. So for the potential drop, we have our crack and our plate. And if we connect a voltage across this, where it would go from, have to travel through this region of the crack. Then as this crack extends, the resistance of the specimen itself changes. And you can come up with a calibrated curve. Again, initially, usually you have to optically calibrate it. But as the crack size increases, this voltage over the initial voltage will increase in some manner, and you can calibrate this so that you can just read the voltage off of this chart and kind of figure out what your crack size is. So there are ways to take these kind of measurements. It's not the main purpose of this course to show you how to take these measurements or talk about them in great detail, but I did want to let you know that there are some various techniques. So with the discussion of the Paris crack growth law, now we have a way to dig into some of our problems in the back of the book. Take a look at the homework problems that are assigned, and do let me know if you have any questions.